This is the 24th episode for VEX for Algorithmic design, and the topic for today is about basic of forces using VEX. I'm going to show you how you can implement a basic physics, specifically a forces in Houdini using VEX and solvers. Now you might have learned basics of physics in middle high school or high school before, but I would like to explain how forces works in order to move the object before going into the actual implementation using Houdini. Now let's say there's an object which has some specific mass and it's falling with the gravity. And this gravity itself is called as one of the force, which will move the object downward. Now the important part is that the force is not actually a velocity, but it's actually an acceleration force, meaning the actual speed how ball falls depends on how much the force has been added as a velocity to this ball. Let me explain how forces works by drawing a circle on an object which is starts with the zero velocity at some space here. Let's call this v equal to 0, and consider that the ball is in the mid-air, like this is a floor. Meaning if we were talking about the Earth's environment, there's a gravity going downward. Okay, let's call this G. And let's draw some timelines like this goes, let's call this T, starting from the 0 time to some time on the right side. So time goes by, the steps goes from left to right. Now in the first frame, when you have a gravity called G, this gravity force is going to be added to this velocity, which is the actual vector value to move the object. Now, meaning currently it's 0, so by adding G to this V, the V will be something similar to this G value. So this is going to be the updated velocity value, the red one. Now by using this one in the next frame, let's call this 1, the object will be moved by the value of velocity by a value of the previous velocity value, and it starts from this moved positions. So the position of the ball has been moved using the velocity as a vector value, in this case downward. Now since the gravity force value doesn't change in any time step, you still have this G value exist, be added to the velocity, and currently the velocity is like this size, but by adding this gravity again to this velocity, you'll have a double size velocity in the next frame. As a result, in the next time step, in the 2, the ball will be moved much farther than the first frame, goes twice as much as far, somewhere around here. And again, you still have this gravity force called G, and currently you have 2 velocity value multiplied by 2, and by adding this additional G to the next frame, you have another velocity added, makes the speed of the falling out faster than the previous frame, and then in the next frame it just touches the ground like this. So what's important here is that the relationship between the position of the object and the velocity, which actually moves the object using the vector value, and the force and the force value, which will be added to the velocity, which is also a vector value. This is the essential relationship you need to remember. First, you have this forces being added to the velocity, then you use this velocity to move the object to a specific direction. And by understanding the basic relationship of this force, you'll be able to easily implement this physics, this force in any kind of environment, including Houdini. And you can of course add additional forces, not just gravity, but if you want to add the wind coming from the side, then you can add a wind force like this, or if you want to have some friction force based on the size of the ball, you can have a friction force going upward based on the size of the ball or something like that. So just by understanding the basic rule how forces works, you can just add any kinds of force you want to move the object. You can also simulate the bounce when the ball touches the ground by reflecting the velocity direction, which was going downward to this way, by reflecting it using the the perpendicular direction with the floor. You can actually create a bouncing velocity. So in the next frame, the ball can move in this direction, the reflected direction. So if you think like this, the forces are pretty easy to understand and pretty easy to implement. And that's what I would like to show, how you can do this in Houdini. And there's a lot of application you can create with this simple idea, so it's pretty useful, I think, especially when it comes to algorithmic designs, using together with the solver for generative design maybe. And today I'm gonna show you how you can implement several kinds of forces and some conditions step by step, building from scratch. Okay, going into Houdini, and first thing I would like to show is how you can implement the basic force first. Let's say a simple gravity using Houdini. Okay, so first I'm going to start with the single point. And let's move the height of this point, let's say to 50, starting from 50. Okay. Now I would like to add a single attribute to this point, which is for the velocity vector attribute. That is because we want to update the velocity at each frame or each time step, specifically in this case using a solver, so that you can add this gravity force to the velocity at each frame. So let's have a node called attribute create. Let's name this velocity. Let's set the type to vector value. And start with the 0 is fine. Now let's create a subsolver. And we're going to use this subsolver to calculate the velocity at each frame and also update the position based on the velocity value. And this first step is going to be the really basic essential stuff you need to remember, how you can create the force, or how you can update the velocity, and how you can update the position based on the velocity. Okay, so let's get inside the solver and let's try to create a point wrangle. We're going to use this point wrangle to control the point velocity and position at each frame. Let's name this gravity force. The first thing I would like to do is to create a gravity force as a vector value, which is going to be added to the velocity vector attribute at each frame. So let's create some variable called gravity with the direction going downward, meaning in this case to a negative y direction. The value could be anything, but don't try to make it too big because it's going to be really fast when it falls. So I'm gonna go with the negative 0.05. You can also change this later. Now, after you have created the gravity constant value, which doesn't change by the frame value, what I'm going to do next is to access to this velocity attribute, which is stored as in the point. If you look at the geometry spreadsheet, at the point, you should be able to see this velocity attribute, which you have created using attribute create. Now what you want to do is to update this velocity by adding this gravity force that you have just created, like this, plus equal. Now, wait here if you have done it, and look at the geometry spreadsheet. Now the velocity has been updated like this. Okay, so before it was 0, 0, 0, but currently by adding the gravity force, it becomes 0, negative 0.05, and 0. Okay, now the next thing you will need to do, currently you have just updated velocity, but the point position doesn't really change right now because you haven't really done with the position yet. So the next thing you need to do is to update the position, in this case at P, using this updated velocity value. What you just need to do is to add this velocity vector to the position vector, and that's all you need to do. And by doing it and going out of the solver, and if you play the solver, you'll be able to see that the points fall down based on the time step or time frame. And you can kind of see that the speed of the falling becomes faster and faster by the time goes by. Previously, at the start it was pretty slow, but the speed is incremented by each frame, so the falling speed becomes faster and faster and faster. Okay, and goes down really quickly. So that's the basic force, how you can implement the force using Houdini VEX. Now currently the point goes like off the floor, so let's also set the floor so that the point will stop at some point. Let's say the y go to 0. Okay, so I'm going to add another point wrangle. Let's say 4. Okay. In this case, it's just the conditional stuff. I'm just going to check the point y value, and if the point y value goes negative, then just fix the y value to 0. So you can do either if conditions, like if at p dot y is less than 0, then fix the y position to 0. And it just stops as soon as it touches the ground. Or you could also make this as one line by writing using a function called max. So at p dot y is equal to max at p dot y and 0. So in this case, it will choose, by using the max function, it will choose either the bigger value in between these two values. And if the point y negative, the point position, the y coordinate of the point position become negative, then that's the case when the 0 becomes larger. So the 0 will be used if the point this goes negative direction or negative positions. So this also works. Let's say like this. Okay. Okay, so that's the basics of how you can implement the forces. The next thing I would like to try to implement is the bouncing. When the ball or when the point touches the ground, I want the point to bounce. And at some point it just stops. So let's try to do this. I'm going to duplicate this first steps that I have created so that I can create a bouncing force or bouncing setup based on this one. And before going inside the solver, I'm going to create a sphere so that we can actually see how the ball, how the point moves clearly by using a copy to points. I'm going to copy the ball or sphere to the moving points like this, so that will be a bit more easier to see what's going on here. So if currently the ball just touches the ground. Now let's go inside the solver And let's see what we can do in order to apply the bouncing. What I would like to do is to change this part, this floor part, to the so that it can create a bouncing force. Okay, so what I would like to do here is to first of all, let's change the name to the bouncing, and let's just delete these. And I'm going to create a condition when the y is negative, then apply a bouncing force. Goes upward. Now let's think about what do we need to do when the ball bounces. So the ball is going to go in, the ball is going down, and when it touches the floor, it has its velocity. And what I would like to do is to use this velocity as it is, but flip the direction which was going downward, but instead when it touches the ground, when it touches the floor, make the direction flips going upward in the next frame. And as a result, in the next frame the ball can move upward, but still there's a gravity force applied. So at some point the ball goes down again and touches the floor again and bounce and go down and bounce and so on. And by continue doing this, the velocity becomes smaller and smaller, so at some point the ball should stop. So let's try this out. Okay, so simply when the point position goes negative in the y direction, I'm going to update the velocity by multiplying by -1, creates the negative direction, the opposite direction, going upward. Okay. And let's also make sure that the point y position is also equal to 0. Alright, so let's see what happens with this. I'm gonna show up this ball, and if I play it, I can see that the ball is bouncing. Let's increase the amount of frames. And you can see that slowly it's changing. It's slowing down, going downward, downward, and downward. But you might have noticed that it's in the air way too long. Consider if it's a real world or real environment. The bouncing continues really a long time. That is because we haven't set any friction, like friction for the bouncing on the floor. So we could try to implement this friction with a simple equations and make the ball goes slower, much slower than the current phase. So let's try to do that. We could go inside the subsolver again, and for the bouncing, currently we are multiplying by -1, but by making this value a bit more smaller, more than smaller than 1, like 0.9 or 0.8, you can make the length of this vector value smaller. As a result, the speed goes slower, so the movement of the position or movement of this ball becomes smaller as well. So as a result, the bouncing will stop faster than this value here by using 1. So let's try to make it as a parameter, like let's make this friction as a flow value, and let's change this value in between 0 to 1, smaller than 1. So let's make this like 0.8 and see what happens. Okay, starting from the first frame, and if I play it, you can see that the speed becomes lower much slower than previous, and at some point the ball just stops like this, just like the real environment. Now if you make it like really small, like 0.3, it becomes much faster. The ball stops much faster, so goes like this. It's a bit this might happen if the ball is pretty heavy. This could also happen, I guess. Or if you try to make this like 0.9. Let's reset the simulations and play it again. Now it stops faster than 1, but at a decent speed. Right. So this is how you can simulate the friction of the floor, the bounciness, how fast it absorbs the force using the floor. Now let's just change this to 8. Okay, so this is how you can implement the basics of the bouncing force. Now sometimes when you do the force simulations, the object which you want to move might not start from the 0 speed, but it might have some initial speed being applied. Initial velocity hasn't already been applied. So let's try to see how we can do this in Houdini. And actually it's pretty easy to do. I'm just going to copy this one. And what you just need to do is to going back to the initial velocity attribute and just set this initial value, and that's pretty much it. Let's say I'm going to set the initial speed to a 0.5 to the x direction and 0.5 to the y direction. So going like this way, starting from this position. So the starting direction is like this direction. And let's see what happens. If I play it, okay. Now you can see that the ball has been going this way as initial velocity, since at each frame the velocity is being updated using the gravity force. So it goes down at some point like this. And it bounces, but there's a bit of problem with the bouncing. It normally when the ball touches the ground like this direction, I want this ball to go this way, but instead it's going the opposite direction, going backward. Now that's the problem with the implementation I did for the bouncing, so let's also fix that. The implementation that I did for the bouncing only works when the gravity is when there's no velocity value in x or z direction, but only for the y direction. But if there's any force, or if there's any velocity value for the x or z direction, I need to change some values for the bouncing. So let's go inside the solver and fix this. So currently the problem is that I'm multiplying this negative value to whole velocity value, both x, y, and z. Now what I needed to do is just multiply the y value because it's going y direction, but for the x and z value it's not going to negative, but if it's coming from the left, then it should go right. So we shouldn't multiply the negative value when it touches the ground. So to make it bounce in a correct way, what we need to do is to multiply the y value by a negative 1. Okay, and for the whole velocity, I'm going to multiply with the friction. Now the friction should be applied to all the forces, all the direction x, y, and z. So we should keep this, but we shouldn't make it negative. So only for the y direction we're going to make it as negative. Now you might have some questions. If the floor is not like straight, if the floor is like this, then how should we apply the negative value? Now in that case, we need to get the normal direction of the floor, and that's the direction you want to multiply the negative value. Okay, so in that case, consider that you need to get the floor normal direction in that case. In this sessions for the basic force tutorial, I'm just going to show you the flat floor, but I'm gonna explain furthermore with a bit more advanced technique with other sessions in other videos. So keep in touch. Okay, now let's check this out. Going back, if I play, now it goes into the right direction and stops at some point. Now until here we were dealing with a single object, but let's say if we want to simulate the multiple objects and multiple balls. So let's see how we can do that. It's pretty simple to do. All we need to do is to first create a bunch of points. So let's try to do this. I'm going to copy this again, the previous set. Okay, now instead of creating a single point, I'm going to create a bunch of points. And to do that, I'm going to start with a circle. Okay. And let's make this up to 50 to the y direction, and let's set this to xz plane. Okay, now I'm also going to set the radius to 5. Also, let's set this to polygon. Right. Now, what I'm gonna do is to add a bunch of points inside or on top of this circle or disk using a scatter node. And you can just choose as many points as you want. I'm just gonna set to like 50 points, right? And then instead of using this attribute create, I would like to set a kind of a random velocity to each of the point, going random direction. So let's create a point wrangle instead and set some randomly created attribute or randomly created velocity attribute. So point wrangle. I'm gonna just delete these and let's name this init velocity. Now, first of all, I'm going to create a velocity based on the positions, okay, which will create a velocity, which will create a vector from the center point to the point position, like these. Now that's a bit too exaggerated, so what I'm going to do, I'm going to now update the y direction or y value for the velocity to 1. Okay, so that it will start, the vector starts somewhere from around here and goes to each of the points like this direction. Now, direction wise, I think it's fine. Now what I would like to fix is the size or the scale of the vector. So first I'm going to normalize the vector, the current velocity vector, and also multiply with some random value so that the speed will be varied. So I'm going to use the random function together with the point position as a seed value. And let's also multiply by 0.5 so that the range of the value becomes 0 to 0.5 as a result. Okay. Now, in the last, I'm going to create a attribute called velocity and apply this velocity vector that I have just created. And let's check this out. We're going into the geometry spreadsheet, and I can, if you see a randomly created velocity value to each of the point, that's good. So this velocity is going to be the initial velocity for each of the point. And let's see what happens with the solver. Okay, so going back and play, you can see the same setup still works for multiple objects. Right, that's pretty easy. So you just needed to add a bunch of points with initial velocity, and that's what you needed to do. Now in the real world, when you try to move the object in the air, in the Earth environment, the movement or the speed of the object is being affected by the size or the weight of its body. Now you might have heard about the term mass. Now mass is used to determine how the object moves based on the forces. Now you might also have heard about the weight, which sounds similar, but it's a bit different compared with the mass. The weight is actually a force itself, but mass is a property of an object. And as I said, the mass explains how fast the object moves depending on its size. So the bigger the mass is, the movement of the object becomes slower, meaning the acceleration becomes slower. And there's an equation called F equal to ma. In this case, m is the mass and a is the acceleration speed, and F is the force. Now in our case, if we are dealing with the gravity, then F will be the gravity itself. And since we haven't set any mass objects or mass properties to any objects, so we can consider it was equal to 1. So meaning, as a result, previously the acceleration was g itself. And this acceleration is the value which was going to be added to the velocity. So what if I change the m value to 2 then? In this case, the a value becomes 2g, like this. So it becomes half the size of the original force, gravity force. And we're going to use this half size gravity added to the velocity, and as a result the movement becomes slower. Previously it was going this speed, but by making the mass bigger for this second object, this speed, the actual speed which is going to be applied as velocity, becomes slower in this case. So this how it works. This is how it works with the mass property. The bigger value you have, the slower it becomes, and the smaller value you have, the value becomes larger, so it becomes faster. So if the mass is like 0.5, then the acceleration value become 2g. As a result, becomes much faster, like this. And I would like to implement this in Houdini, and let's see how we can do that. Now let's try to implement this in Houdini. I'm going to again copy this previous set. And first of all, I'm going to set an initial mass to each of the point as an initial value. I'm going to make it as a randomized mass for each object. Let's say in between 1 to 3. In between 1 to 3. So after I have set the velocity, I'm going to also set the initial mass. And probably it's easy to understand by changing the size of the sphere based on the mass as well. So I'm also going to set the p-scale as well, so that you can use it with the copy to point subnode. I'm going to set as init mass, and first of all I'm going to create a random value called mass using random function based on the point position and probably using some seed, custom seed parameter. Okay, promote the slider. This by adding a seed, you'll be able to randomize the value that you're going to be created. Now, what I'm going to do is to fit or remap this mass value using fit 0, 1, since the random value in between 0 to 1, and 2, 1, 2, 3. Okay. And then I'm going to set this value that I've just created as a p-scale as well as the mass float value. Okay, so currently the object size looks like this. Some objects look smaller, some objects looks bigger, like that. And let's also increase the number of points to 100 so we can have some more variations. All right, now let's also check going into the geometry spreadsheet for the point, and we see this mass property or attribute going from around 1 to 3. All right, that's good. Now let's go inside the subsolver and try to use this mass attribute to change the force value. Now if we go back to these equations, F equal to ma, and currently the F is equal to the gravity, right? And the actual acceleration value that I want to get is this a value, which is going to be added to this velocity. So if we think like that, the actual a is F divided by m, like this, right? And so by dividing this gravity value by the mass value, you'll be able to get this actual acceleration value, which is going to be added to the velocity. So let's try to write these equations in Houdini. I'm going to show up the gravity force, click the gravity force here, and then first of all I'm going to retrieve the mass attribute and then use it to divide with this gravity value here. So let's create a vector called acceleration, and then that value will be gravity divided by F at mass. Okay, and this acceleration that I've just created is going to be the one that should be added to the velocity. So do like this, and the velocity will be added to the point position to update the point. And that's all you need to do. So let's leave the solver and let's see what happens with the simulations. If I play it, you can see that the bigger objects move slowly and the small objects move faster. And the bigger object has a bigger mass. So bigger mass, by having a bigger mass, the object speed goes slower. So that's how you can control the mass. Based on the mass, control the force value. Like this. Now that I have implemented the mass property, the next thing I would like to do is to try to implement the air friction. It's pretty similar to what we did for the floor. For the floor, we have applied the friction when the ball touches the ground or the floor. But for the air friction, it just happens at every frame when the point is in the mid-air. So you can just call the friction or use the friction at every frame, every time step. So that's the only difference. So let's try to see how we can do this. I'm going to copy this set again. And for the friction part, I just need to do inside the subsolver. So let's go inside the subsolver. And let's try to add another point wrangle somewhere. Since we are using this gravity force to update the point position, we're gonna create a friction beforehand. So point wrangle, and let's name this friction or air friction. Now the basic idea for the air friction in this case, if the ball falls like this, and if the ball is in the mid-air, I want to add another force to this setup, which goes the negative direction of the velocity. So let's say the current velocity is going this way, but by having this air, there's some force going to the negative direction and can be set as F in this case. And probably this friction value will be changed based on the size of the object, but in our basic setup we're not going to consider the size of the object, but just consider the friction for any size of the object. Probably in the real world, if the object is bigger, there's more friction than the small one. So if the size is bigger, then there's more frictions going on for a bigger object and less friction for the small object. But let's forget about this for now, and let's try to see how we can set this base friction force. Now, since we want to add a additional force to which is going negative direction to the velocity, first thing I would like to do is to create a attribute called friction and retrieve the current velocity. Okay. Now what I would like to do now is to update this friction value by first of all normalizing the velocity value, the current velocity value, and also make it negative, so going into the negative direction, and then set some friction speed or force, friction force value. Let's make this as a parameter, and let's call this like 0.005, something like this. Okay, and then update the velocity by adding this friction value as a force. Okay, so that's what I want to do. Alright, now going back and see what happens. Now let's try to check from the previous one without the friction how it looks like. So it goes like this. Okay, so it stops around 500 frames. Now if you do this with the friction, air friction, it stops much faster than without the friction. So by adding a negative directional force, it quickly goes full downs rather than going outward like this and create and stops pretty fast like this. So this is another technique to make the simulations a bit more realistic. Okay, and if you want to consider the size of the object as well, then you could go back here and try to change this friction value based on the size as well. So as I said, more size. If you have more size, then you might be able to have more friction. So in this case, you can try to multiply the p scale and see what happens. Now p scale itself is just a radius, so it's not the correct size. It doesn't really shows the correct two-dimensional size, but let's just fake it. Okay, and if I play it, now the bigger object becomes much more slower. And the whole object stops much faster. Okay, but that didn't look that realistic, so I'm just gonna get rid of this one. Okay, so here's that, the one with the air friction. Okay, now in the next example, I would like to show how you can set a bit more conditional friction. Like, let's say if you are throwing the balls into the water. Now, obviously, the speed of the ball should slow down because of that. And that is because of the friction from the fluid. So let's try to implement that kind of situations. When you slow in the balls, as soon as it goes inside the water, the speed of the balls slows down because of the friction. Now to do that, let's start by creating some conditions, like when the position or the area where the water is. Okay, so I'm going to copy this setup again. And let's create some box first. Act as a water tank or something. And let's set the size to 100 by 20 by 100. And set the center to 10. So the box becomes like this. Okay, now we would like to make it as a water tank. Now I am going to convert this into a SDF, just like the session, just like I did for the last sessions. The SDF is pretty useful to determine if the point is inside that SDF object or not, SDF volume or not. So I'm going to convert this into SDF by using BDV from polygon. Okay. Now let's set the voxel size to a much bigger size because currently the resolution is a bit too high. It's around 1000. Yeah, that's too high. So let's set it to 2. So now it becomes 50 by 15 by 55. That's totally enough. You can make it less, much less as well, but let's just do with this. Now I need to check this fill interior. Okay, now, and since I would like to use it as a guide to check if the point is inside this box or not, I'm going to connect this to the second input of this solver. Right. Now, as final setup, I'm also going to make this box a bit transparent. So I'm going to use a point wrangle to set a alpha attribute, which you can set the transparency or opacity of the object inside a preview. So I'm going to set the alpha as like 0.3 or 0.4. So you can make it as you can control the opacity, and then let's merge it with the final output. The final bowls position. Alright, so it's good for the setup right here outside the solver, and let's go inside the solver to actually calculate the friction. I'm just going to reuse this air friction, so instead of air I'm going to use water friction. And this time I'm going to use this SDF as a guide to check if the point is inside the box or not. And only if the point is inside the box, I'm going to apply the friction. So I'm going to connect this to the second input of this water friction. And going into the water friction, first thing I would like to do is to check if the point is inside the box or not. Okay, so first of all, I'm going to check the SDF value by using a volume sample coming from the second input with the surface with the current point position. Now, if the point is inside the SDF volume, then the value should be negative. So only if the SDF value is negative, then I would like to apply diffraction. Okay, so let's create the conditions. Now, other than that, it's pretty much the same as the air friction. You just need to get the current velocity and then multiply it by some flow value like this, and then apply it or add it to the current velocity. Now, since it's inside the water, the friction must be higher than the air, so let's say it's around 0.2. Let's see what happens. And other than that, let's just keep it as it is. So keep the last bouncing as a flag, a display flag, and let's see what happens. If I play it, as soon as it goes inside the water, it just slows down. Now there's a little bit of jittering here, right here. It's a bit weird. It might happen in a real world, but it's pretty weird, so let's try to fix this. We can fix this by going inside, and previously I was using a normalized friction, a normalized direction to set the friction size, but instead we can just use the current velocity value. Or let's say we could just skip this part and say negative current velocity multiplied by the friction. And by doing this, you'll be able to skip or you'd be able to avoid the friction or the jittering, I mean. So let's see what happens. Okay, so if I play it, that looks more natural. So as soon as it touches the water, go slow down. And when it touches the floor, it just stops. Now I didn't consider the radius of the sphere to touch the ground. It just used the center to touch the ground to consider it touches the ground. If you want to consider the radius as well, you need to add some conditions to the bouncing node somewhere around here. Since we are using p scale, we can say f at p scale, and we could set this p scale here as well. And let's see what happens. If I play it, now it uses the radius to touch, consider that touch the ground. Right, that looks good. Now the next example I'd like to show is to introduce a external force other than the gravity, like a wind. So let's see how we can do that. As I said, the external force can be applied same as the gravity. You just need to introduce some additional like vector values and use it to add it into the velocity at each frame, and that's all you need to do. So I'm going to copy this previous set again and delete some of the stuff which we don't need. We're not gonna use the friction this time, so I'm going to delete this one and keep it as it is. Okay, we don't use this one. Now, since I'm going to introduce the air, I am going to go inside the subsolver and let's also remove the water friction as well. And instead I'm going to introduce a wind force. I'm going to create a new point wrangle. Let's set this before gravity force and let's name this wind force. Okay, now first of all I'm going to set the direction for the wind. So let's say I'm going to move to the x direction, right? So I can just say create vector value wind set 1 0 0, right? Now maybe we could also set the size of the wind or the speed of the wind, okay, by setting some parameters for this value, for the x value. So let's say wind, and let's set the size to pretty small, a bit smaller than the gravity. Currently the gravity is 0.05, so I'm gonna set it to 0.01 or 2 or something like that. Let's see what happens. Now what I just need to do, I just need to add this wind to the velocity, and that's all. Oops. That's all you need to do. Pretty easy. Alright, so let's see. Let's see what happens. So currently the wind force has been introduced to x direction. And it goes like this. Alright, so it seems to work pretty fine, pretty good. It just moves the x direction. I just added the x directional force and that's all I did. But it does look like you have added the wind force, and the balls just stops when the velocity reaches to 0. Alright, looks good. So that's for the external forces. And for the final examples, I would like to introduce another external force, a bit more complex than the wind. The wind was just the one directional force, but this time I would like to use a volume to introduce a turbulence force being applied to these balls. Okay, so let's end this session with this final force. Okay, so I'm gonna copy this again. And what I want to do first is to create a turbulence vector volume. So let's do that first. I am going to first set some boundary for the turbulence so that it covers this balls. So let's create a box first to set the volume. So I'm gonna set the size to 100 by 50 by 100 and set the center to 25. So the size is like this to cover the sphere, like this. Okay, now I'm going to create a volume out of this box using a volume node. And then let's name this, let's set this to vector volume, and let's set the name to vel. And let's set the initial value to 1 just to see how it's been, how it does look like. Now, in terms of the resolution, it's okay to have a low res, I think, but doesn't change the speed that much, so I'm gonna change to 50 to have a decent resolution. Okay. Now, what I'm going to do now is to create a turbulence-like velocity vector from this volume to this volume, applied to this volume, and also changed by the time. The movement changed by the time. Okay, so that's what I would like to do. Or maybe I don't really need to change the volume by the time. If I could just create this rotational turbulence vector value from the center, then that could be just fine. So let's try to do that. I'm going to use the volume wrangle to modify this volume values. I'm gonna name this turbulence. Now, since I would like to create kind of a rotational vector value, first thing I would like to do is to get the create the attribute called val coming from the point position. Now, if it's a point position, then it's always the vector value is always from the center point to this point position in each voxel. Now, in that case, the y value is not necessary, so I'm going to set the y for this vector to be 0. Okay. Now, and the size is all different. If it goes far from the center, the size becomes large in this case. So I'm going to normalize this so the size will become 1. Okay, now I'm going to set the y value again to make it a bit more jittered, so that you have some randomness on the y direction. Okay, so for that I'm going to use the noise function based on the p and some scale value like 0.01, could be any value, and then the value you get is in between 0 to 1, so you might want to have a negative direction going downward as well, so I'm going to subtract by 0.5. Now I am going to multiply this back with a bit higher value like 5. Now I'm going to normalize this again so that the whole vector size will get reset to 1 again. Now the next thing I'd like to do is to currently the basic direction is going this way from the center to outward. But what I want to have is this rotational direction. So in order to convert this direction, omnidirection, to a circular direction, you can just rotate the vector value by 90 degrees, either to clockwise or counterclockwise. So to do that, I'm going to use a matrix. First, I'm going to create an identity matrix, then create the rotational matrix using a mat with the pi point multiplied by 0.5, which creates 90 degrees in radians. Then use 0, 1, 0 as a rotational axis. Then finally, I'm going to rotate this velocity using this matrix and update the volume velocity with the velocity vector that I have just created. Alright, so with the preview, you cannot really see which direction is volume is facing. So in order to check this, I'm going to use a volume trail to check in which direction the vector volume has been created. I'm also going to create a scatter node to the volume to starting the trail, and let's see in which direction the trail is going. And as you can see, you have this kind of a rotational turbulence like vector field created from the inside the volume, and that looks totally good. Let's increase the number of points. So it's not bad at all. Looks good. Yeah, we can totally use this to move the object. So what we want to do next is to use this vector field that I've created to this vector volume to retrieve the turbulence force and use it as a turbulence force inside a subsolver. Okay, so I'm going to connect this turbulence vector field or vector volume to this second input of the solver, and let's go inside. Now, previously I have this wind force, but instead I'm going to change this to a turbulence force, and from a volume and retrieve the vector value from the volume. So turbulence force, and this is the volume. So let's connect this to the second input of this turbulence force. And all you need to do, first of all, you need to get the vector value from the second input, the vector volume from the point positions, from the ball positions. So you can get that by saying vector turbulence is equal to volume sample v. From the second input, the name of the vector velocity volume is vel, and from the point positions. Okay, now you can set currently the vector that you're going to retrieve is normalized, so you also need to set the size, or you also need to set the speed of the force, the size of the force. So let's multiply this turbulence with some parameters. Turbulence, and finally add it to the velocity, just like you did for the wind. Okay, so let's set turbulence to 0.01, and let's also delete this wind parameter, which you don't need it anymore. Okay, so that's it. That's pretty much it. And if you go back and check how it moves by playing, you can see that the ball is moving like based on its turbulence force instead of the wind, instead of one direction. All right, so that's it. That's how you can create a bit more complex external force using a vector volume. And this is it for today's session for the basic of forces using VEX. Today, by implementing several forces, I have shown you the basics of physics, how you can easily implement it using VEX code together with the subsolver. And the idea can be extended for many purposes, so the things that I have shown you here is pretty essential. Please remember how you can do this. And for the next sessions, I would like to extend the idea and try to introduce more of extended forces, not just with the basic stuff that I have just shown you today, something like an angular force or wave-related force, such that to have a bit more extended idea for the basics of physics, which could be really useful as well. So I hope you could check that out as well. If you like this video, please like the video, and if you are not yet subscribed to the channel, please do to check out the upcoming videos. And I've also started the Patreon page myself. You could go from my description page on the YouTube video. If you would like to support me, I would really appreciate it to continue what I'm doing like this. Okay, so thank you very much for watching, and I hope to see you next time. Bye.